Hi everyone. Okay, so today we'll be talking about the Math 17B discussion sheet 2. So if you remember back to week 2, we did a drip lab. And so here we thought about definite integrals in order to keep track of how many drops had dropped out of the water bottle. If you remember the setup, it looked something like this. And we had water dropping into a basin, and we were timing, and we wanted to keep track of how many drops had dropped based only on the rate. So we kept track of the rate, and you counted how many drops dropped in 10 seconds over 5 intervals, and then worked out the drop rates, and then worked out how many drops you expected to have fallen in 2 minutes for each of those. Okay, so we counted the number of drops, and so when I counted 22 drops in the first interval, 10-second interval, then 20 drops, and then 18 drops, 16 drops, and 14 drops. So then the number of drops we expect per second, for 22 divided by 10, you get 2.2 drops per second since we did 10 seconds, and then 2 drops per second, 1.8 drops per second, 1.6 drops per second, and then 1.4 drops per second. Now, if we multiply by 120 seconds, we'll get the number of drops that we predict to fall in 2 minutes. If I do that, I get 264 in the first interval, 240 in the second interval, 216 in the third interval, 192 in the fourth interval, and 168 in the fifth interval. Now, obviously, those will differ. If you counted a different number of drops, you might be correct. Your drip rate would be correspondingly different, and then your number of drops would be different. So that's fine if you differ slightly from this. Okay, so now we want to calculate how many drops have fallen since the beginning of the experiment. So a lot of people were kind of tripped up by this table. So one thing that we really want to focus in on is the fact that here the time since the start t in seconds. So here we have 0 seconds, so 0 drops have dropped, right? So 0 time after the start. We haven't measured any drops, we haven't let any time go by, there'll be 0 drops, okay? So then here at 120 seconds, we have 396 drops. So notice 396 is 3.3. The rate from the first 120 seconds is listed right here, and then we multiply that by 120 to get the number of drops here. Okay, so we're always, when filling in end drop, we're always going to look back for the rate, because that tells us the rate for the past 120 seconds. Okay, so here first we should fill in our calculated rates. So I calculated in the 13th minute 2.2, and then 2.0 in the 15th minute, 1.8 in the 17th minute, 1.6 in the 19th minute, and then 1.4 in the 21st minute. Okay, so now filling in our blanks here. So to get the number of drops by the 480th second, we take the drops by the 360th second, and then we take 120 times the drop rate in that interval from 360 to 480, which is 3.0. It's listed right here. So we'll take 3.0 times 120, which is 360, plus 1,140. That's 1,500. Okay, so you should definitely agree with me here. There should be no difference. Here we should get 1,500. And then adding to 1,500, 120 times 2.5 gives us 1,800. So again, these should be the same up till the end of this row. And then here we'll get 2088. And notice this should still be the same as what I have, because we've been given the rate. We multiply this by 120 and add it to what we had previously. So up till the end of this row, you should have the same thing in end drop. Okay, and then you can start to differ slightly, because to get the entry of end drop for the 840th second, at the end of the 840th second, you'll take 2088 and add whatever your rate was here in the 13th time interval times 120. So when I do that, I get 2352 Okay, now of course you'll just fill in. So again, always go back. I get 2592, and then 2808, and then 3000, 3168, 3300, 3420. Okay, so that takes care of part A, part B, and now on to part C. So a physical model of the system says that the drip rate should be linear with time. That is, our drip rate R of t is some linear function, so that's given by the y-intercept R0 and the slope C. And R0 and C should be positive constants. By fitting our data, we can determine the constants R0 and C. Okay, so we're going to use RStudio to find the line of best fit. Okay, so we need to find the line of best fit. So first, we need to tell the computer or RStudio what our data is. So to do so, I'm going to first tell it that what time is, right? I'm going to define the time list. So time is a sequential list, right? So we've taken the time at 0, 120, 240, 360, so we're counting by 120, and we're going from 0 to 1560. So here in defining a list sequentially, I say seek from equals, so I'm going from 0 to 1560, and then by 120. Okay, so now I've told the computer, now in T, hold on to a list, and it should have everything from 0 to 1560, counting by 120. So I press enter, and I look over here into my environment, and I see that now T holds a list of numbers that is 14 entries long, and it counts 0, 120, 240, 360, and it goes all the way up to 1560. Okay, and now I need to hold my R data, my rate data. So R, now notice these aren't evenly spaced. It goes 3.3, 3.2, 3.0, and depending on what you enter, they might be different. So you need to enter each of those, and the way that we tell the computer that we're entering a list that is not sequential, that we're going to just tell it all of the entries, is we use this C command. So R is a list, and in the list is 3.3, 3.2, and actually, if you want to get something that you've typed before, you can use your up and down keys to access old entries. So I've done that here so that I can just grab a hold of, I already typed R in at a different point, so I'm going to grab R here. So now R, if I hit enter, holds all of these rate entries that we calculated. So 3.3, 3.2, 3, 3, 2.5, so on. Okay, so now if you want to find the line of best fit, you need to tell the computer how to think of the data that it's put in. So the call for finding the line of best fit is lm r, whatever that is, twiddle t. And so what that's telling the computer is pretend all of the R data is a linear function in T and give me the model that best fits it. Okay, so when you press enter, you get back this return. You can ignore this first part, but it tells you the coefficients. So it says the intercept for this line, thinking of the R data as a linear function in T, the best line that fits that model, it has y-intercept 3.4 and slope negative 0.001676. Okay, so now we need to tell the computer, okay, cool, we've got these coefficients, now we need to actually define the function that is the line of best fit. Okay, and the way that we do that, so I'm going to name mine R line, and I say R line is 3.4 minus, and you're going to enter it just like you would, write down a line, right? So 0.001676 star t. Okay, now this star t, remember t is a list. We already entered that. And the cool thing about R is that it can do all of these operations on all of the entries of a list all at once. So what this is going to do is access all of the entries of the list, multiply by 0.001676, and then subtract that from 3.4. So it's defining a new list that is the corresponding values of this line for the entries in T. Okay, so if we hit enter, notice now our line is a list of numbers that's 14 entries long because T was 14 entries long, and all of these values correspond to what was in T times negative 0.001676 subtracted from 3.4. Okay, so the good news, or sorry, not the good news, the good thing that RStudio can do is plot both of these things simultaneously. So the first thing we have to do is tell it to plot. So we tell it to plot T and R, and it always goes X value first, Y value second. So T is our X value here, R is our function value. So when I hit enter, I get a plot, and these are all just the data points. Okay, now if you want to add something to your plot, like for example, this line of best fit we just defined, then you use the command lines. So lines just adds a linear piece of data to your already created plot. Okay, and so what it's going to do is it's going to take all of these points in our line and T, the corresponding points, and it's going to plot them and then connect them by a line. And since our line is a line, it'll just be a line. So T, our line, add it, and we get this line of best fit. Okay, so now we've plotted the line of best fit, and we have that. So just a reminder, the line of best fit that I calculated was R of T is 3.4 minus 0.001676 T. Okay, you should have something somewhat similar if you have anything varying by a lot or not a negative sign here. Check your work, you probably have a problem. Okay, so part D says that we know the integral of a line, it's this m over 2 s squared plus bs. So we're going to use this equation and the model for the drip rate to predict what the number of drops is. Okay, so we have that the rate is some linear function, and so the idea here is that n drop of t is the integral from 0 to t, so of r of, and I'm just going to insert a variable that's not t here so that I indicate that it's not what we're integrating over, right? Because this is what we're going to plug in at the end. So r of s ds. So we're going to integrate all of the rate over the interval from 0 to t, and that'll give us the number of drops at time t. And this makes sense, right? So if I tell you, in second 1 the rate is this, you would multiply that rate by 1 second and then add that to, the rate at second 2, so on and so forth. And what the integral does is it just takes smaller and smaller intervals, right? So it says we're getting instantaneous rates, and when we integrate those, we're going to get the number of drops that's fallen by time t. Okay, so I have what r of s is, so I'm just going to insert that. So it's the integral from 0 to t of 3.4 minus 0.001676. Oops, sorry, I'm going to put in s here, ds. Okay, now integrating that using this rule, I get that this is 3.4, that's b, times s, minus, now this is my m over 2, so 0.001676 over 2 times s squared. And then, of course, I evaluate that at 0 and t. Okay, now plugging in t, I get 3.4t minus 0.001676 over 2t squared, minus this stuff evaluated at 0, but when I plug in 0 here and 0 here, that causes the whole thing to go to 0, so it would just be minus 0, so I don't write it. Okay, so my predicted end drop is 3.4t minus 0.001676 over 2t squared. And you should get something relatively similar to that. Okay, so now we're going to use another way of checking that our estimate of the drop number is kind of on track. Okay, so in the experiment, the height of the water in the bottle was also measured, and we knew the cross-sectional area of the bottle. So if we estimate the volume of a drop, we can use these measurements to determine end drop T using the volume of the water that we know has come out of the bottle by a certain time. Okay, and so someone did this for us. They filled in this table. So time since start T, and then this is end drop using the estimate based on the volume. Okay, so this is how many drops we think have fallen based on how much volume is left in the bottle, given the height of the water in the bottle. Okay, so now we need to make a plot of end drop T as a function of time, and we're going to plot the data given here. We're going to plot our estimate from the first problem, and then our estimate in the second problem. From the integral. And then we're going to plot them all in the same graph and see which one fits this data best. Okay, so we're going to plot the data from problem 3a, the data that we calculated in part 2b, and the integral that we calculated in N2D. And then we're going to see which one fits best the data in part 3a. Okay, so first I'm going to enter this data that we've been given in N3a. Okay, so these are all of the entries of the end drop estimation via the volume. Okay, and so when I hit enter, I see up here we have a list of 14 numbers, and in it is the entries of from end drop. Okay, and oh, of course I need to add time. So T is a sequential list from 0 to 1560, counting by 120. And notice we should always check and make sure that the length of our lists match up. So here this is 14 inches long, or sorry, 14 entries long. This is 14 entries long. So we can only plot things that are of the same length. Now let's enter the data from N2B. So these are the values that we calculated when we were guessing that the rate was constant over the 120-second long interval. Okay, and again we get a list of 14 numbers. Now let's enter the function that we calculated in part 2D. Okay, so here is my negative 0.001676 over 2, and then I put that in parentheses so that I can multiply that by t squared, and r does squared just like you kind of expect with this caret and a 2, and then plus 3.4 times t. And whenever we have times, we always use a star. Okay, so if I hit enter, okay, it took all of the values in t, put them through my function that I just defined, and put them into N2D. So here I get exactly what I want. Okay, and now I'm going to plot T and N3A. So this is the data points that we were given in via the volume for part A. And when I hit enter, I get this nice smooth curve. Okay, and now I want to see which lines fit better between the estimation from 2B or our integral we calculated in 2D. So I'm going to use lines to add T, the 2B data points. And this last just tells me I can define a color here. So I'm going to put in red. So the data from 2B is now red. Okay, and we get this nice smooth curve. And then let's add the data from 2D. So remember, this is our integral. And I'm going to color this purple, And notice this purple fits better. So when we got our data from 2B, remember that we were counting the drops from the first 10 seconds of our time interval, which was 120 seconds long. So the rate that we measured and considered constant over that 2-minute long interval was from the very beginning of the interval, right? And so then afterwards that rate slowed down, although we ignored the fact that it slowed down. So of course, here in the image we see that we're over counting the number of drops, or overestimating. And that's because as we went on, the rate was slowing down, but we didn't keep track of that. We just took the estimation from the very beginning. So it would be sort of a left endpoint estimation. Now, the integral fits closer because we decided our rate was linear, and we took into account this linear decrease in the rate when we did our integral. So of course this fits closer to the volume estimation. Okay, on to problem 4. So in part 2D, you integrated a model for the rate to find the number of drops that are accumulating. Now show that if we differentiate the number of drops, we'll get back the rate. Okay, so remembering that our rate from, n drop from part 2D was 3.4t minus 0.001676 over 2t squared. If we differentiate that, so dn drop over dt, we're going to get 3.4 minus 0.001676 t. The 2 comes down and cancels, and we just get t. And this is exactly what our r of t was from before. Okay. Now, problem B, from a physical perspective, does this make sense? Should the change in accumulated drops per unit time be equal to the drip rate? Absolutely, right? The number of drops that are accumulating, if you could measure that instantaneously, that would be exactly the drip rate. Okay, now problem C. Notice that n of t is the integral, the number of drops is the integral of the rate, and the derivative of the number of drops is exactly the rate. So that's exactly what we know from the fundamental theorem of calculus. And so since we had that the rate was linear, we could solve the integral on the left and find the number of drops by asking ourselves, what function has derivative the rate, this linear function? So if this relationship remains true, what would the number of drops be if r was some quadratic function, r0t minus ct squared? Okay, so what they're asking us is, can we integrate this quadratic function? And now you definitely can, but before you could too. You just had to ask yourselves, what's the antiderivative of this? So if we have r of t, so if we have r of t is r0t minus ct squared, okay, so then taking the antiderivative, we get r0, so obviously we're going to go up a power here, and then we have to divide by 2, right? So that when we take the derivative, that 2 that comes down will cancel with this 2, and we get back r0 times t. And then we're going to do the same thing here, ct cubed, right? We go up a power, and then we divide by 3, because when we take the derivative here, we'll get a multiplication of 3. That'll cancel with this 3. And so our corresponding n of t would be r0t squared over 2 minus ct cubed over 3.